In this video, we will talk about projection and rejection between vectors in any dimension. Of course, it also applies to the case 2D and 3D. We start with two different vectors, vector x and vector a. And we want to decompose vector x into two different vectors. The first is the vector parallel with a, and the second vector is the vector that perpendicular to a. So our task is, given these two vectors, x and a, in any n dimension, we want to find x parallel in this figure and also x perpendicular in this figure, and both x parallel and x perpendicular is a vector. And we will show you in this video that the answer is for x parallel is equal to x dot vector x dot vector a with geometric product inverse of vector a. For the vector x perpendicular is equal to vector x wedge product vector a, and then close parenthesis, geometric product with inverse of vector a. In this slide, we will try to decompose vector x into superposition of two different vectors with the help of vector a. So let us start with vector x. And we can also always write vector x equal to vector x geometric product 1, which is just x equal to vector x. But we also know that 1 is equal to, can be written as geometric product a, geometric product from vector a to vector a inverse. So then we'll write vector x, vector a inverse. Since geometric product is associative, so we can calculate, instead of calculate a and a inverse, we can calculate vector x, geometric product vector a, then a inverse. And geometric product from a vector to a vector can be expressed in terms of dot product and wedge product. This means that we can express x dot a plus x wedge a minus 1, geometric product a minus 1. And geometric product is associative. No, it's also distributive. So we can also write x dot vector x dot vector a, geometric product a inverse plus x vector x wedge vector a, geometric product a inverse. And now we express the x into two different vector, and vector x is the superposition of the vector here and vector here. And now we want to to the next slide, we will want to show that this is actually x parallel, like here, like the vector here. And also next, and also also we will show that this this vector is also corresponding to the x x perpendicular to A, the vector x perpendicular to A. So now we want to show that the x parallel can be indeed written in this form, that x dot A geometric product A inverse. How we do that? We start with this expression, that A dot x dot A and we also want to realize that x can be written x parallel plus x orthogonal. So we can write x parallel plus x orthogonal dot A dot A, and we know that the x parallel dot A plus x orthogonal, we know that this one here, since x by definition x orthogonal is orthogonal to A, so this part go to 0. So we have x parallel dot A but one important point is that x parallel okay, I should write it here. One important point to know is x parallel wedge A is equal to 0, because since they are parallel to each other, the wedge product will always give you 0. So I can plus 0, I can always plus 0, but instead of 0, write 0, I write x parallel wedge A equal to. So now you can see that we have vector x parallel dot A plus wedge parallel wedge A. So we can write the h. No, we can write x parallel geometric product vector A. Then you can see that here we have x dot A also equal to the geometric product x parallel, geometric product from x parallel to A. So let me write it down here. Equal to x dot A. Then we can do the inverse on both sides. So we end up with x dot A x dot A so yeah we can write the x parallel into this form with the combination of the dot product and the geometric product here. Now we want to show that x perpendicular can be indeed written in this form, that the starting parenthesis vector x wedge vector A close parenthesis geometric product vector A inverse. It will basically be the same tactic we have in previous slide. we start with x wedge wedge a, and we also know that x equal to x parallel plus x perpendicular. So let us write x parallel plus x perpendicular, and okay, this wedge a it will be equal to x parallel wedge a plus x perpendicular wedge a, and we know that this is 0, so it will be equal to x perpendicular wedge vector a, and we also know that x perpendicular dot product with vector a is equal to 0 since they are orthogonal in any dimension. It can be 2 dimension, 3 dimension, but they are defined to be orthogonal because this is pretty much the symbol we mean here, orthogonal. By orthogonal we mean that this x vector orthogonal component is orthogonal to a. So we can add 0, and instead of write 0, I write x orthogonal dot a equal to then this is equal to x orthogonal geometric product a. So what we have turns out x orthogonal geometric product a equal to x wedge a. Then we can rewrite this. We just geometric multiply on both sides of inverse a. Then we get x wedge a and geometric product minus 1. And now we have, from our derivation, we have x parallel equal to x dot a and a inverse, x perpendicular can be x wedge a geometric product with a inverse. So we want to think about in the case of 2D, in the case 2D, and x will be written in e1 and plus x e2, and in the case of also the vector a will be a1 e1 a2 e2, and in the case of 3D, so x will be, I will just write it in this way, x that I equal to 1, then this sum to 3, okay, and a will be equal to 1 and equal to vector a equal to the summary starting from 1 to 3, then a. Yes, and of course in n dimension, x will just be I equal to 1, this to n, x I e I and vector A will be just I equal to 1 sum to n AI. Yeah. And we realize on this basics vector, and they have length 1 and they are orthogonal to each other. So now you know how to, when you given a vector, you're given two different vectors, you can immediately find the you can use one of the vector to decompose it to another vectors, and that is the expression how you do it.